This is question Q2b. We'll ask you to first generate xn and then use DFT to find the DFT coefficients using DTFS to find DTFS coefficients and then DTFT coefficients from DFT coefficient xk. Basically, in these questions, we are asking you to use MATLAB or Python to generate xn. Now, this is xn. The equation that we're interested in is the cosine pi over 3n sine pi over 4n. Remember, we found that n is equal to 24. Over here, we have plot 2 period of it, 48. We can see that it repeats every 24 samples over here. Now, I'm going to plot it in two ways. Basically, one's using a stem and the other one is using a plot. The stem will give rise to the vertical lines you see, the green thing, and the plot will only put the crosses on there. Now, remember that our n starts from 0, and then of course, because we start from 0, it must be 2n minus 1 samples. And then after that, we use the dot times in MATLAB to make it generate as a vector. However, please be careful. When we want to extract one single period, MATLAB indexes the vectors starting from 1. So we need 1 to n, not 0 to n minus 1. So it's very strange and you have to get used to this problem. In Python, it's fine. Python uses index from 0 for its array, but MATLAB uses 1, start index from 1. Anyway, once we have generated x and we have extracted one period, so x underscore p is the one period, we simply use FFT in place, which is exactly the same as this DFT. FFT is the fast version of discrete Fourier transform. That's it. And then we have a coefficient xk. Remember, this is a vector of Rn. Here is Cn, a complex vector with n elements. So now here again, we are going to need an index from 0 to n minus 1, because we are going to plot the stem from 0 to n minus 1 for a horizontal axis. And we're going to extract absolute, which is nothing but the magnitude of the coefficients. And then we're going to use this guy, stem again, showing us that we are using 0 to n minus 1 for the index. And then we're extracting using angle to get the face. Now, this guy here, the first guy, which is the blue one, you realize that I only want to plot the angle when the magnitude is greater than some very small value, which is 1e minus 5. And lastly, I'm going to divide everything by pi so that the angle is with respect to pi. So it's half pi, so it's 0.5 will show up instead of 0.5 times 3.1416, which is pi. Okay, so I'm going to show you the plot from using this figure. So there will be two plots. The top plot is the magnitude, the bottom plot is the angle. Okay, where it is? It's here. So first is the magnitude on top, here the angle below. We start, this is 0 to n minus 1, so n is 24, so 20, 21, 22, 23, here's 23. Okay, so this is stem of k, right, from k, and then we have the absolute value of the xk here. This is the second one is the stem k, and this is the angle over here. Alright, so what when I say that the angle is with respect to pi, can you see? This is minus 0.5 times pi, because I've divided by pi in my calculation. So you see it's minus half. Minus half pi. Okay, that's what it means. Alright, so we have the magnitude and the phase. Now this is the index going from 0 to 23, which is n minus 1. This is the single-sided spectra. I'm using 0 to 2 pi here. I can also plot 0 to pi and minus pi over here. This is the double-sided spectra. So 0, 1, 2, this is 3 here, and this is 4. This guy will be minus 3, and this guy is minus 4. So you realize that the double-sided spectra are typically what you see for CKs. So you have C3, C minus 3, C4, C minus 4. And then you can see that this is the place where we have the sine wave, because the phase is opposite of each other. It's a little bit more strange to see it in the single-sided spectra, but actually they are totally the same. So let's see how we generate the double-sided spectra. The equation for the double-sided spectra is to use something called the FFT shift. Go and read about FFT shift manual, and basically it shifts the high guys to the other side. Okay, and of course we also need to case shift as well the index, right? Because now the index go from minus pi to pi, and we have to show it as integer versions of the k. So which is minus n over 2 to capital N over 2 minus 1. Now put the ceiling there, otherwise it doesn't work for even or odd. Okay, so the first figure, the top one, 211, means the top figure is stem of k shift, FFT shift absolute. And what about the bottom one, 212? This is stem of the k shift, so showing you the horizontal axis and the FFT shift of the angle value. Again, the angle value is the original angle value of xk, and then because I only want, what do you call that? I only want it to show for absolute xk greater than very small value. If you don't do this, you'll see a lot of numbers coming out when you know actually it is due to numerical precision. And divide by pi so that along the vertical axis, then this is, you know, something easy to read. Alright, now do you make a mistake? I guess it's minus pi over 2, right? So this should be minus pi over 2, so this point should be minus half. So I'm going to change that for you. This is plus half. Okay, Ken, thank you.